So I'm going to show you how to analyze feedback circuits and how feedback can be used to design amplifiers that have predictable gain, even though the components we use to design the amplifiers themselves may be unpredictable. I'm assuming you know how to analyze a circuit like this and get an expression like we see here. The gain of the amplifier depends on a lot of things. It depends on the operating point. We know that if the signal is too large, the non-constancy of the gain, the nonlinearity, will cause distortion. We know that the relationship between the source and the load impedance causes a variation in the gain, and the voltage division between the output impedance and the load impedance. All those things are generally unpredictable, and in particular, they are frequency dependent. So it's a reasonable question, how is it possible to design amplifiers that just work? Gain tends to be temperature dependent, so how is it possible to make the gain of an overall system temperature independent? How do you get the biasing to be right? How do you get those input impedances to be what you want? And the answer is really one of the most important things in all of electrical engineering, maybe in all of engineering, and the answer is we use feedback. So how do you analyze a circuit with feedback? The classic way is the way I'm going to show you now. This circuit is called the non-inverting feedback amplifier. This is an operational amplifier. We see it's got an input source and an output voltage. And the steps that you would go, a classic way to analyze this circuit is to first take the amplifier and replace it by its equivalent circuit. We have a control source with an input here and an output there with a gain A. And we write V out, this voltage is equal to A times the input voltage. And we're just going to do some algebra on that. We can substitute VI as VS minus VF. And we can get VF as a voltage division as a multiple of V out, or a fraction of V out, given by this formula. Notice that we've got V out on the right-hand side. What we really would like to have is V out on the left-hand side and not on the right-hand side, just things on the source. If we expand this a little bit, we can do what I like to call this algebraic maneuver, is like the feedback maneuver. You take the thing that's on the right-hand side, multiply it out, and then subtract from both sides in such a way that we get V out onto itself plus this function of itself. I'm going to divide through by that factor, and the next term that I get is what I need. I've got the closed loop gain, the ratio of V out to Vs, as just a ratio with no other terms there. And this is the form that we end up with. We can express this factor of called beta as the feedback factor. The amount of the output that is fed back to the input, we'll call that beta. In this case, it's R1 divided by R1 plus R2. A we'll call the open loop gain, and the closed loop gain, A, is the overall formula. This is one way of expressing it. There's another way that is a little more general. If you take this form and then divide both top and bottom by A beta, you can convert it into this form. You can let A beta be what I call the loop gain, 1 over T. If T is sufficiently large, then this factor drops out, and we get that the closed loop gain is just A infinity. In that case, this would be 1 over beta. And when I say A infinity, we're going to be using this. It's the value of the closed loop gain you get if A goes to infinity. And the key point is that if A is sufficiently large, then if the loop gain is sufficiently large, then the overall closed loop gain of this thing doesn't depend on A. That's the main point here. If A is sufficiently large, it doesn't matter how large it is. The closed loop gain of this amplifier will be determined entirely by the ratio of these resistors. And so that's the answer. This is how we can do this. And we can see that designing amplifiers is really about, that have stable gains is done by using feedback. All right. So I want to break this into simpler terms. This analysis that we were using for this is sometimes called the A and beta approach. It works fine for this example, but it doesn't generalize very well. A lot of circuits just don't split cleanly into parts A and beta. It does here, but it doesn't in all of them. As you'll see if you go through this, the results depend on a bunch of assumptions you make about the amplifier, and it's Actually, it turns out not all feedback circuits are amplifiers. And then when you use this technique, some of the results you get are just wrong. So I'm going to show you a different way of doing this that's simpler. It doesn't involve a bunch of rules or anything. It's just you follow this procedure and it's very general and it doesn't depend on whether it's an amplifier. It also breaks the analysis into several pieces. You do one analysis and find the loop gain. You do a separate analysis and find the A infinity gain, and then you combine the two. That's a very design-oriented technique that breaks us down into easier analyses. So first, let's find out how to find the loop gain, what I call T. You take the amplifier, you replace it by its linearized equivalent circuit. You then turn off all independent sources. So we had an input source over here. I replace it with its internal impedance. The internal impedance of the voltage source is just a short circuit. If this had been a current source, it would have been open circuited. And there's the circuit we're going to analyze. So what I want to do then is choose a branch that all the feedback signal flows through. The signal flow is clockwise around this circuit. And I can break this circuit anywhere I want in any branch that has all the feedback signal flowing through it. I've chosen this one just arbitrarily here. You break that branch. Feedback signal flows clockwise. That means that this feedback loop has an input port and an output side. And we're going to treat this as the input now to an amplifier. We'll call this the X port, and the one over on the right we'll call the Y port. We apply a voltage source to Vx to the input port, and we need to find the resistance seen by Vx. In this case, I'm going to call it Rix, and in this case, it would be R1 in parallel with R sub I plus R2. And I'm going to make a copy of Rix, and I'm going to put it across the Y port. And this is the circuit we're going to analyze. We're going to find its gain. The gain of this amplifier is T, and it is the loop gain. I'll worry about the signs of the gains later. We're going to need it to be negative feedback, and we'll say more about that. So this circuit can be analyzed using standard techniques. When you go through it, you get this formula for it, but the most important thing is you just do this analysis. So you could have broken the loop in other places, and you would have gotten the exact same answer. So this is important. T is a very important property of any feedback circuit. T is independent of how you find it, and it's independent of where any input's applied. We turned off the input source. We don't care where the output is. It's a property of the circuit, independent of its inputs and outputs. Let's summarize. We take the circuit. We represent it by its linearized equivalent circuit. We turn off all independent input sources. We choose a branch that all the feedback signal flows through. You break that branch. You find the resistance looking into the input port. You make a copy of that resistance and place it at the output. And then you find the loop gain by analyzing what's now just an amplifier without feedback. Now the other part of the analysis is to find the gain A infinity. A infinity is the gain from whatever your input is to your output when the control source gain A goes to infinity. Now, that sounds a little complicated and a little scary maybe. What does that mean? It turns out to be a very simple thing that's easy to interpret in terms of the circuits. If this control source gain is infinite, assuming V out, which is A times VI, is finite, you can rearrange that equation to get V in equals V out over A. If A goes to infinity, it should be clear that VI goes to 0. And that is the assumption we're going to make. So when we say that A is infinite, we really mean that the input voltage goes to 0. The second thing that comes out of that is whatever this input resistance is, if the voltage across this resistor is 0, that means that the current flowing into this resistor is 0. So this gives us a second and third assumption or a condition, and that is that these two currents are both equal to 0. And if you think of this as an op-amp, then these become what are called the ideal op-amp assumption. The voltage across the input terminals is 0, or which is to say that V plus equals V minus, and also that IN plus and IN minus are both equal to 0. That simplifies the circuit. So once you do that, you can to find the gain, you use these ideal op-amp assumptions, and then you just go around and figure out what that means about the circuit. In this case, because the two voltages are equal, this voltage Vs is equal to Vf. So Vf over here is the same as Vs. You know that in order to use voltage division, you have to have that the currents in the two resistors have to be equal. The fact that this I sub I is equal to 0 by this assumption means we can use voltage division. So Vf is just V out times the voltage division factor. And since Vf is equal to Vs, that means that V out over Vs is just equal to 1 over this factor. And so the closed loop, or A infinity is the closed loop gain. If A goes to infinity, which is to say we have these ideal assumptions, and it's just 1 plus R2 over R1. The thing that's nice about this is that you can apply this A infinity approach to any feedback circuit. You don't actually have to have an op-amp. In general terms, A infinity is just the value of the overall source to output gain when the signal that's controlling the control source is forced to 0 because of the infinite gain of the control source. And the key thing is that assuming infinite gain gives you a simpler circuit analysis. And then once you've got T and A, you can find the overall gain just using this formula. And this 1 over T business in the denominator is a measure of how ideal is the circuit. You say, well, it's not really an ideal op-amp. Well, how ideal is it? This expression is the answer to that question.